Okay, so today I'll be giving an introduction to general relativity. It's going to be at the, I guess, second year level. It's not going to be very in-depth. Some of you might already actually know this if you took undergrad relativity or if you've done some readings on your own. So we'll talk about, so ignore that slide. So flat space-time. So flat space-time is basically, it's called Minkowski space-time, so anytime you hear someone say it's in Minkowski, it's just talking about flat space-time. The line element is the equation we show here, which is basically like Pythagorean theorem, but it's in 3D and it also includes the time component. And the reason why the time component is negative is it comes from a thought experiment with light, and it actually makes everything work. If we didn't have that, none of the equations will work out. So it's a pretty simple derivation. If you want to know more about it, let me know after the talk. So something about Euclidean and non-Euclidean geometry. The flat space-time metric, or line element, is non-Euclidean. But the way we think of Euclidean versus non-Euclidean is that in our world, the shortest path to get somewhere is just a straight line. But in non-Euclidean space-time, it's actually the curved path that takes us the shortest time. So one of the classic examples is these two triangles where you have A, B, C on the first one and A prime, B prime, C prime on the second one. And one of the first questions you are asked in an undergrad relativity course is which path is shorter to get from A to C? In Euclidean spacetime, of course, it's A to C, the hypotenuse. Nothing surprising there. But if you're in non-Euclidean geometry, the shortest path is actually taking A to B, B to C, because due to the negative sign in time, they actually cancel out, so the path length is 0. And A to C prime is actually the longest path. So that's how curved spacetime works. It's not the way we usually think about it. Something about 4 vectors that are basically the same as, they're just vectors in 4 dimensions of space, like our metric. You can usually sum them up in this way, where you usually bold text it or put a tilde under it. That means it's 4D. And then you have your component, which is A alpha, and then you have a basis vector, which is E alpha, which is what you've learned in our undergrad courses. Alpha here, because it's a Greek letter, it just goes through time, X, Y, and Z. If you have a Roman letter, like say I, that just means you're going through space, so it's Y and Z. And so another way we can expand this is by writing it out this way. So for each component in our 4-dimensional vector, and we usually write flat space-time as this. So on the metric I showed beforehand, you just take the components from your ds squared. So ds squared is just the distance from 2 points. That's all it's saying. So you take your components and you put them in front of all your basis vectors, and you eventually get something that's a matrix, because since you have your xx, xy, xz, or xt in front of that, and then you have a 4x4 matrix. And so you just take the diagonal of that, and the rest of it is 0, and then you have a symmetrical spacetime, 4D spacetime. The dot product, that's supposed to be an alpha. So the squares are actually supposed to be alphas. I wish I could use LaTeX, really cool. So whenever you do a dot product, you are used to seeing this in physics 1. You have your component and then your basis vector dotted with the same, but for another vector. And so what you want to do is to get a metric, you want to put your basis vectors together and your components outside, and the basis vectors can be used to describe eta, alpha, beta, which is just your flat spacetime metric. So it just gives you the basis for your geometry. And then that eventually leads to describing the distance between 2 points in spacetime as eta, alpha, beta, and the change or you can write it as the velocity of alpha and the velocity of beta. So that's another way you write ds squared. You only write ds squared, I think, in special relativity, really. Once you get to general relativity, you use tensors and components a lot. So again, the scores are supposed to be alpha. So our metrics, our flat spacetime metric is always denoted as eta, alpha, beta. Whenever you see a g, alpha, beta, that means it's some general metric. you can change the components of it. For example, here you have flat space-time but in polar coordinates. So you have your diagonal components for time, x, y, and z. This is symmetric, so you have zeros on the others. It doesn't have to be, but for flat space-time, it's symmetric. And then in order to find the geodesic equations, you can find that from some metric. So here you have, this is actually the wormhole metric. So you have your time component, your r, your theta, and your phi. And you just write it in the Lagrangian form, which if you take in classical mechanics 1, or actually 2, you get to it in 2. You know what the Lagrangian is and how to calculate it. So it's basically just derivatives. And so you use the components from your metric, from your line element, and write it into a Lagrangian. And then doing some math, taking the integral, you end up finding the components for each coordinate. And from that, you're actually able to, you can't see it directly all the time, but once you get to general relativity, you'll be able to see that the equation of motion for a particle around some geodesic is equal to the negative of some Christoffel symbol times 2 velocity components. And you can see from this equation, you can guess the form of this equation. But you will actually derive this in general relativity. Again, if you want to see any derivations or any specific problems you're interested in, let me know and I can go through it with you. I can send you some resources. So that's really cool that from some metric, some random metric, you are able to see how test particles can go around some desired spacetime. And so the most basic geometry is the Schwarzschild geometry. It's the simplest spacetime we have. After that, it starts getting really complicated. And so this is the metric for it. So it has some properties. So just from looking at the metric, you can see that it's time independent. So that means none of these components for your time, r, theta, and phi depend on time at all. So whenever something's independent of some component, we call it a killing vector. So a killing vector is actually denoted by z. And in this time, in this case, because we're independent of time, our killing vector is equal to that diagonal of 1, 0, 0, 0. C is just the way we use the killing vector. So you will see that in more advanced courses, and the way that helps is that you have less stuff to solve for. So we always try to find what a system is independent of and the symmetries we have, because it really simplifies the problem. Another property of the Schwarzschild metric is that it's spherically symmetric. And so you see that if you have, so here for example R, it's very symmetric, it does not depend on phi, it only depends on theta. So you can see that just by looking at the metric. And another thing is that you can expand mass, so if you have 2gm over c squared, if this component is small enough, that means you can expand it and rewrite the line element in this way, which makes it a lot simpler. You take out the negative sign and you have a plus sign there. And so R here is not the radius. It's not saying from the center of the, or from the singularity to some event horizon. It's just giving you it's related to the area of the black hole, but it's not like you're measuring from the center of something to the outside. So it's a little bit of an abstract concept. And then you have singularity. So what you can notice here is that when R equals 0 and when R equals 2gm, you get a singularity. So the problem with that is that now what we know is that a singularity is only at the very center of a black hole, if you can say that. But the reason why we have a singularity at 2m is because that's actually the event horizon. And the way you can get rid of that singularity is by transforming this to another coordinate system. So we have the Finkelstein-Eddington coordinate system. Finkelstein's actually an emeritus professor here. And by doing this change of coordinates, you are able to eliminate the singularity at r equals 2gm. C and G's are actually, we usually just make them equal to 1. So this is kind of an exception. So this is actually, the units are correct here. But we usually just say 2m over r. So, so that's the simplest metric. And then gravitational waves. So gravitational waves are just small perturbations in space-time. It's given by some metric, you have some general metric, g alpha beta, and you just have your flat space-time plus some perturbation in the metric. And some sources of gravitational waves are supernovae, mixed binaries such as two black holes, or you can have two black holes, two neutron stars, black hole and neutron star. You can have even like our sun and then a black hole, and pulsars. This is actually a picture from an X-ray picture of the Crab Nebula pulsar. So it was basically a star, and then it exploded into Corpulop supernova, and what you get is it's a pulsar, which is just a rotating neutron star, and it's giving off some beams. And the physics of pulsars is actually not well understood at all. It involves some QED, quantum electrodynamics, and it's just very complicated to understand the object. Even neutron stars, we don't even know what the equation of state for neutron stars are. So they're very complicated objects. And so my last slide is basically about binary black holes, because that's what I know the best, and I didn't put any equations. Oh, I forgot something really important actually. I'll go back to it. So for this equation, a Christoffel symbol, what it is, it's a connection in a manifold. So this just depends on the derivatives of your metric. So basically what you have is your Christoffel symbol is equal to some metric times a ton of derivatives from your metric that just have permutations. So it's it's a little bit of an abstract concept, but you'll understand it more when you go to it.
Thought it came from the Riemann tensors, which are derivatives.
The what tensors?
The Riemann tensors.
Riemann?
Yeah, Riemann.
No, the Riemann quadratic tensors can be written in terms of Christoffel symbols and the metric. The Riemann quadratic tensor tells you how much curvature there is in space-time, or I guess derivatives of that. And then you can find that, you can contract it and get the Ricci tensor, and then you can get the Ricci scalar, which tells you how much curvature you have, if you have any at all. Oops.
And can falsely say you don't know. And can falsely say you don't know.
Yeah. Yeah. So binary black hole. So this is just going to be kind of a little bit of a spiel about my research. So binary black hole systems emit gravitational waves. Those are actually the strongest systems we know that emit gravitational waves. Gravitational waves travel at the speed of light. We know that for sure, but we need to know the signal. We need to have an understanding of the signal in order to actually detect these gravitational waves, which is an effort that some of us at Georgia Tech are involved in with LIGO. And so this is actually from the 1980s maybe, this picture. So before we were able to solve Einstein's equations, this is what they thought gravitational waves would look like. So here you have two black holes orbiting each other, emitting some radiation. Then you have them getting closer to each other and emitting the most radiation. And then you have both black holes just settling down into one final black hole, which is smaller than the mass of the two initial black holes. So this is what they thought a gravitational wave would. That H here is just the strain of the black hole. So basically when you have LIGO, you have two perpendicular arms. You have a Michelson interferometer. And the strain is just a change of the length of one arm over the actual length. And so that's what strain is. It's usually in the order of 10 to the negative 24 in units of strain, which is 10 to the negative 18 meters. So in reality, what you have is some sine wave here for the merger of the black holes while they're rotating around each other. And it's mostly a perfect sine wave, except that it tells you a little bit about the orbits of the black holes. So it tells you how eccentric it is. And so once you get to the merging, you actually get a spike. I should put a picture of that in here. You get and our time is in solar masses because that makes more sense. So you have some merger, and then you have black holes merging, and then they merge into one black hole. And so this is actually really off from what we thought it would be. It looks really, really bad. And so in 2005, we were finally able to solve the space-time for two black holes colliding. So numerical relativity started in the 1950s, the golden age being in the 1960s. And so people were just trying to figure out how to evolve two black holes in space-time, and how we can get, like, how to solve Einstein's equations in a computer and everything. And so we didn't have the computational capabilities for that beforehand. So until 2005, we were able to solve for both black holes actually merging, and the computational costs are extremely expensive because you have a really large parameter space. You have to look at resolution, and the resolution changes as the black holes get closer together. And then you have a problem at the singularity where you have to use different methods like excision and puncture. And so, but those are things that have already been solved. Now we just solve Einstein's equations with different parameters, which still takes a lot of money and time, and generate these waveforms. So these waveforms can take weeks to months to generate, each one of them. And so in those waveforms, we're able to know everything about the system, the mass ratio between both black holes, the spins, the initial, the radius of extraction, so where they began to orbit each other. We're able to find the modes. So what's really important about gravitational wave signals is that you can decompose it into modes. So these modes just mean the sky location for LIGO. So LIGO is blind in some spots, and it's most sensitive in the perpendicular direction to its both arms. And so the thing is, when we detect gravitational waves, once we decompose them into modes, some modes will not be as strong, and you can even ignore some modes and still recover just as much information. For example, the energy radiated. So one of the modes that we know well to radiate the most energy or tell us more about the system is a Tutu mode. And so that's just kind of the lingo that if you ever hear about modes, Tutu is always the one people use the most. And then some modes don't even contribute anything, so you can just ignore all of them. So the reason why it's important to know more about these modes is that we are able to maybe make some computations or something just using those modes and not wasting computational time and money evolving systems and taking into account the other modes. We can kind of just ignore them. Another thing is that the greater the mass ratio between two black holes, the less energy they radiate. Because if you think about it, if you have one black hole that's a lot bigger than the second one, the biggest one's going to be in the middle, and it's going to be orbiting a little. It's not going to be moving much. But then you have the smaller one going around it, and once it merges, it's not going to perturb the bigger black hole that much. So it's not going to radiate as much energy as if you had two black holes of the same size. And if you add spin to the system, you'll have a lot more energy radiated. So what we found, our group, and I think some group at RIT, is that black hole systems, binary black holes, can radiate as much as 12% of their total mass. So if you have 250 solar mass black holes, and then they merge, you'll only end up with like 88 solar masses of mass from the black hole. So that's a lot of energy that's radiated, and I once did a calculation, and it was like, you can light New York City for like more than 4 years with like 1% of energy radiated or something. So it's just a lot of energy that is going on into gravitational radiation, and it's a window for a new way to see the universe. We've only seen it in electromagnetic. We can see the CMB, but this will tell us more about the system. And so some other groups the groups here at Georgia Tech are working with the waveforms and trying to find some of the parameters from these systems by using the least amount of components needed. So maybe just by cataloging all of the waveforms into same mass ratio, just using that one component, it will make it easier for detection, for the people detecting to know what parameters we're looking at. So once you get the gravitational wave signal, you have some waveform. Oh, great, what does that do? So actually getting out all the information from that one signal can take months. So using some principal component analysis, you are able to just take the components that matter the most, maybe 2 or 3, and then you're able to pop that out really quickly in like probably a few minutes or less. So that's my talk. Thank you very much.
The mass ratio determines how efficiently they can radiate energy.
Yes.
And then when they're equally massive, like exactly equally, there'd be no gravitational waves, right? Because it'd be symmetric.
No, yeah, they do radiate gravitational waves because they are accelerating as they're orbiting each other.
I thought they were formed off anti-symmetric properties. I thought
I mean,
specifically you have to have something that's anti-symmetric about your origin. Or
well, gravitational waves are just caused by anything that's accelerating. So if they are moving around each other.
Well, I know the reason why some neutron stars, like, they don't necessarily do it on their spin is because they're so uniform around them, like, they have
I
very
mean,
small
if they
perturbations.
bulge out.
Yeah,
right?
I mean, that's how they create them, but like, if they're completely spherical, you wouldn't have that, so in
Right, if it's just static or
symmetric,
spherical, yeah.
it doesn't matter if they're the same mass and the orbits would be completely symmetric.
It doesn't matter. Any other questions?
You mentioned that 1% of the energy coming out of these gravitational waves could power New York for 4 years.
Yeah.
Is there any possible way in the future that we could harness that energy as another source?
I don't think so. I mean, I know that that's a big, it's like a hot topic, but I'm not sure how realistic that is, and I'm not even sure how they will do that.
Right.
So,
It's in the form of gravitational waves, so you have
yeah,
to like.
but they're so weak. They're
Yeah.
like,
Yeah,
the change,
well,
like,
unless you're close to it.
10 to the negative 18th meters. Yeah, like you will need, yeah, no, we don't have anything that's close enough to create a really strong gravitational
You basically
wave.
need something that will be able to harness the energy of changing size on a oscillation.
Right.
Yeah, that would be cool.
Yeah.
But you have to be really close to the source.
Yeah, which will be really problematic.
Yeah.
If you see Interstellar,
Well, and then you also have to have a way to get the energy away from away from the black hole, which would take a lot.
yeah, it can take up like billions of years for them to just get close, like while they're going around their center of mass, it can just take so much time. And once you get to basically merger, it can take a few milliseconds.
It's basically like milliseconds.
Microseconds, 2 microseconds, yeah. So it's a really quick merger.
That's a problem for engineers.
So,
Oh, that'd be cool. If we had relativistic engineers in the future.
You actually have to understand physics.
I did not say
Please let
that.
us record it.
For the recording, it is recorded.